Welcome to this section in physical science on conservation of energy. And in this video, we're going to talk about four main ideas. First of all, the conservation of energy. What does that mean? We're going to talk about energy transformations, power, and a little bit about calories. And we've already mentioned this in previous videos. The law of conservation of energy states that energy cannot be created or destroyed. You know this. It can be converted from one form to another, or it could be transferred from one place to another, but it cannot be created or destroyed. Ways that we're going to look at for energy to be converted or transferred would be energy transformations. And here are some examples: transferring chemical energy into some kinetic or energy of motion, radiant energy into chemical energy via photosynthesis, electrical energy into thermal energy as heat, and a whole lot more. So let's start looking at some of those energy transformations. Before we get into discussing specific energy transformations, let's just look at a phrase that gets used a lot in science and in our society, and that is conserving resources and conservation of resources. Do not be confused with the fact that energy is not created or destroyed. If we quote unquote save energy, we are it's not that we're using the energy up and it's gone if we don't. I want to discuss this for just a minute. The total energy always remains constant, but the usefulness of the energy definitely changes. The form that the energy is in may be more useful in certain forms than in others. For example, there is chemical potential in gasoline. A huge amount of chemical potential in the gasoline. When you drive your car, you use that chemical potential up and transfer that into mechanical energy to make your car work. You also transfer a lot of that into heat energy that sort of warms a little bit of the universe right there, right around where your car is. That potential energy converted into thermal energy that warms the air and mechanical energy when driving your car means that the chemical potential energy is no longer available to you, to anyone. It's gone. Does that mean the energy's gone? No. The energy was converted into thermal energy and mechanical energy. Chemical potential energy is no longer the form that that energy is in. So when we say conserving resources, it doesn't mean that we are literally somehow saving energy, because if we don't save energy, we'll use it all up and it will be gone. No, we are simply keeping the energy, or trying to keep energy in its useful form as much as possible. And not use up all of the useful forms of energy that we have available to us. So the usefulness or the form of the energy, and different forms of energy have different usefulness. So obviously that thermal energy that we warmed the air with is not very useful to us any longer. And so the total energy, however, remains constant. So now let's get into some specific energy transformations. Let's look at some very specific kinds of energy. Mechanical energy is where we're going to start. And when we talk about mechanical energy, we are talking about the sum of all of the kinetic and potential energy of the objects in that system. Is the mechanical energy. The mechanical energy includes gravitational potential energy and elastic potential energy, if that exists in the system. Mechanical energy does not include nuclear energy from the nucleus of an atom, thermal energy in the form of heat, or chemical potential energy. It does not include those different items, those different kinds of energies. And mechanical energy is not the total energy of the whole system. It is only the sum of the kinetic and potential energy of the objects in the system. Mechanical energy alone is not conserved. The total energy in our system will be conserved, but mechanical energy can be transformed into other forms of energy. Therefore, mechanical energy itself will not be conserved, but the total energy, of course, is conserved. Here are just some examples of mechanical energy, falling objects, projectile motion, and swings. And let's look at some of these specifically, or each one of these individually. So let's look at the mechanical energy in a falling object. What is going on? Let's start by looking at this apple right here. It has a lot of potential energy, gravitational potential energy. It has a certain amount of height from the ground. G, due to gravity, is a factor as well in calculating gravitational potential energy, and it has mass. So it has a lot of gravitational potential energy. It doesn't have any kinetic energy right now. Its mechanical energy is that large amount of gravitational potential energy and no kinetic energy, right? That would be pretty close to zero. As soon as that apple just starts to fall, let's say it's just starting to fall down, it will have a little bit of kinetic energy. Some of that gravitational potential energy is being converted into this kinetic energy. And at this point, it has a small amount of kinetic energy, and it still has gravitational potential energy, which is a little bit less than it was just a moment ago because its height is a little less from the ground. In another moment, we'll experience the same thing. This apple will have some gravitational potential energy plus some kinetic energy. There will be a little bit more kinetic energy at this point than there was a little bit ago. And that will continue until right before it hits the ground, where it will have entirely a lot of kinetic energy and very little gravitational potential energy left. The overall mechanical energy of this system remains fairly constant. Yes, energy can be transferred in and out. We have air resistance. We have some thermal energy transformation happening from the mechanical to thermal energy because of friction from the air resistance. But overall, mechanical energy tends to remain fairly constant within the system as we're adding this gravitational potential and kinetic energy as this object is falling. Now let's take a look at what happens to the mechanical energy during projectile motion. When that pitcher first throws the ball, it has a lot of kinetic energy, very little potential energy yet. As that ball travels to the top of its trajectory, it is going to begin to go a little bit slower in the vertical direction. As it rises higher and higher, the force of gravity pulls on it, and it travels a little bit slower vertically until it reaches the top of its trajectory, where it has zero vertical velocity at this point. So at that point, it would have very high gravitational potential energy and very low kinetic energy. As that ball continues to travel down to the ground on its trajectory, it will continue to increase in velocity. Remember, we have the acceleration due to gravity acting on it and the force of gravity acting on it, and it will travel faster until it reaches this point where it will have very low, right before it hits the ground, very low gravitational potential energy, but very high kinetic energy. So let's take a look at the mechanical energy and how it is behaving when a person is on a swing or when there is the motion of a swing. If we look at a little graph, a little bar graph, comparing the kinetic energy and the gravitational potential energy, you know that when the swing is right here at the height of its trajectory, really, right here, at this point, there is little to no kinetic energy. That swing is just has stopped and it's changing direction. So this is almost entirely gravitational potential energy, kind of going along with this graph. Likewise, at the other side of the swing as well, this graph will be the same for this position on the swing as well. What about when the swinger is right in the middle, or the pendulum is right in the middle here? At that point, the swing is engaged almost entirely of kinetic energy, right? There's very little gravitational potential energy. Just to the side here or the side here, there might be just a little bit of gravitational potential energy, but most of that energy has been converted into the kinetic energy at this point. And what about positions here and here? Well, they would be in between these two graphs. There would be something in between about half potential, half kinetic energy, half potential, half kinetic energy right here as that pendulum is swinging on its way to its different positions. So let's take a look at some energy transformations. We've been talking about mechanical energy. Well, did you ever wonder, why do you have to pump on a swing? If energy is conserved, shouldn't I just put a bunch of energy into my swing and then I should just keep going forever? That would be nice. However, there's something called friction, the force of friction, that prevents that from happening. And the force of friction transfers some of the mechanical energy into thermal energy. We have friction here, where the physical mechanism of the swing is hooked onto the pole here, and every time that swing goes back and forth, just a little bit of that mechanical energy is converted into some thermal energy. There's also the force of air resistance, converting the mechanical energy into some little bit of thermal energy. Therefore, in order to keep that swing going, you have to keep pumping more energy into it from your body, that you're using chemical energy from your food to convert that into energy so that you can pump your swing and keep this swing going. Anyway, that is one energy transformation that happens. If there were no force of friction whatsoever, that swing would continue to go back and forth, and that mechanical energy would not be transformed into thermal energy. What's another energy transformation? Well, remember electrical energy? Electrical energy can be transformed into thermal energy. Think about your toaster or your stove. How about electrical energy being transformed into radiant energy or sound energy? You know that from your television transforms electrical energy into radiant energy and sound energy. Your computers, there's a lot of things that do that. We have this transformation, electrical energy into mechanical energy. The electric motor in the washing machine does this for us, and we get mechanical energy with the motion of objects in the drum of that washing machine. How about radiant energy being transformed into chemical potential energy? Plants do this all the time through the process of photosynthesis. We also have chemical potential energy in the gasoline being converted into thermal and mechanical energy. These are just some examples of energy transformations, different types of energy being transformed into other types of energy. It's around us all the time. It's happening constantly. Pause the video for just a minute. Jot down some of your own ideas, some of your own examples where you are observing energy transformations around you. We've been talking about energy. Now we're going to talk about a word called power. A lot of people have a lot of different ideas. What is power? There's a lot of different pictures here showing power. I have the power. What does that mean? What in the world are we even talking about when we talk about the word power? In science, power has a very specific meaning, and let's look and see what that is. Power is the rate that energy is converted. So we're going to talk about this a little bit more. Just to backtrack and review, remember, energy is the ability to cause change. Work transfers energy. And when we have energy that is being converted at a particular rate, the speed at which that is converted is our power. That's what power is. So we can talk about power as being equal to energy per or divided by time, the amount of energy converted per time. We measure energy, remember, in joules. We measure our time in seconds. Joules per second has a special unit, and it is called a watt. Power is measured in watts. So here's our nice little formula. Remember, capital P, not lowercase p, because lowercase p, remember, was momentum. But we have capital P for power equals energy divided by little t for time. So let's try a problem using the idea of power. How much electrical energy does a 5-watt light bulb convert to radiant and thermal energy in 1 hour? Well, let's start by writing down the things that we know. We know one thing. We know that we have a 5-watt light bulb. Remember what watts measures? Watts measures power. So we know our power is equal to 5 watts. We also know the amount of time we're talking about. We're talking about time equals 1 hour. Ooh, problem. Didn't we say our time needs to be in seconds? Yes, time must be in seconds. So we need to do a little conversion and make sure our time is in seconds. If we multiply 1 hour by our conversion factor of 60 minutes equals 1 hour, we get hours canceling. That gives us the number of minutes. If we then multiply by the next conversion factor, 1 minute is equal to 60 seconds. We get our minutes canceling, and we know then that our time of 1 hour equals 3,600 seconds. Seconds is the only unit remaining. So now we know our power and we know our time. What is it we're trying to find? Well, we want to know how much energy is converted from electrical to radiant and thermal energy. So energy is our big question mark. Let's write down the formula that relates all of these different variables to each other. That's our power formula. Power equals energy divided by time. This is simply a plug and chug problem. We can plug values in and chug away and find our answer. We know power is 5, so we can put a 5 watts right there. We know our time is 3,600 seconds. Time can be substituted there. From here, where do we go? We want to solve for E, for energy. So if we multiply both sides by 3,600 seconds, and this will be a little messy on this side, but bear with me. These terms cancel, and I can simply say my energy is equal to 18,000 joules. Remember, energy is measured in joules. One last point to mention when we're talking about energy transformations, and that has to do with calories. You've all heard about calories. What are calories? Why do we talk about calories and not talking about dieting? And a lot of times that conjures up visions of, oh, I can't eat calories. What is a calorie? A calorie, literally in science, is equal to an amount of energy, a specific amount of energy. It's the amount of energy required to raise 1 gram of water 1 degree Celsius. That is what an actual calorie is. We use calories a lot of times when we're talking about energy conversions in our bodies. How many calories does our body use? In other words, how much energy does our body use to do certain functions? Here's a little chart showing different functions and how many calories an average 150-pound woman might use, how much energy she would need to, or she would use to do some of these different functions for a given amount of time. Chemical potential energy of food gives our body that energy. And 1 calorie is equal to about 4,000 joules of energy. It's a different way of measuring energy, a different unit, but this is about what it is equal to. And one important thing to note is that a calorie in science is not the same as a calorie on the package of your food. Those are actually kilocalories. And the number of calories on the back of your Cheerios box, when it says, there's so many calories in this much of your food, it's actually the amount of energy needed to raise 1 kilogram of water, 1 degree Celsius. It's technically a kilocalorie, but they just abbreviate it scientifically incorrectly on the back of all of those packages. So what do you need to know from today's video? You need to know the law of conservation of energy. Never forget it. It is the law. Know about energy transformations. Know about mechanical energy. And know about all different kinds of energy transformations, how the different forms of energy are transformed from one form into another. Know how to calculate power and the definition of power. Know what calories are and what we're talking about when we talk about calories. Some advanced ideas, great ideas for you. If you have other ideas, please feel free to explore your own questions. Come in, show me what you know, and I'll mark you off for advanced proficiency. Look forward to seeing you in class.